Today, this video will show the analysis of a converging diverging nozzle for the fluid air. To begin with, we are going to use the fluid flow Fluent. We'll create the geometry first of the converging diverging nozzle. To begin with, we're going to select the XY axis, and since this will be a 2D analysis, these will be our dimensions for the nozzle. So we have 200 meters from the center to the top and bottom. From the size will be 1000 millimeter, and then again on the outlet we'll have the same 200 millimeter up and then 200 millimeter down. From the midpoint we'll have 50 millimeter as a guiding line for the nozzle. We'll remove these lines. Now we have a sketch of our diagram, and we're going to give it a shape, clicking fill on the top here. So now we have our diagram, and now we'll head on towards the mesh. Here on the right we'll select the 2D analysis, since the 3D analysis takes a lot of time for converging. And now we're going to click mesh here. Now we have our mesh. We're going to click here, go to mesh control, click face meshing, select the geometry, click apply, going to mesh control again, click sizing, select the geometry and click apply. Here we'll set the element size to 0.004 and we'll update. Now once we click on this mesh, we can see that we have our element sizing, and when we go to statistics we can see the number of elements. Then next we are going to define our boundaries. This one will be named as inlet. Then we have our outlet on this side. These edges will be named as wall. We'll click update and we'll head on towards the next step. Click here double precision and click OK for the setup. Our analysis will be density based and not pressure based, so we'll choose density based in this, and then we'll head on towards models. We have the equation on, we'll have the viscosity as the inviscid flow, click OK. We head on towards materials. We're going to choose air. In this option we'll choose ideal gas, change, create and close. Now I'll leave my colleague to explain furthermore on the analysis.
Thank you, Samir. Now we will proceed with the boundary conditions specified for our problem. We go to boundary conditions, and Our inlet is a pressure inlet, so we make sure to change that to pressure inlet. The values are as follows: atmospheric pressure for the inlet 11325 pascals, and have the same thing for supersonic gauge pressure 11325. And the thermal, the inlet temperature is 300 Kelvin. Now our outlet is an outlet. Make sure the type is pressure outlet, and this would be 99348. So we have a subsonic flow. Click OK, and operating conditions would be 0 pascals. Change this to 0 pascals. Now we make sure that the wall, we specify the type is wall, so the solver knows. Outlet is pressure outlet and inlet is pressure inlet. Now we go to reference values to double check our values from the inlet. So we know that the temperature is 300 Kelvin, the velocity, inlet velocity is 0, and the pressure is 11325. Density from the ideal gas formula. For the methods, keep it the same, controls the same, current number 5. Now for residual, to have a better, more accurate results, make this 0.0001 for all the values. Click OK. Now we initialize. So in initialization, we go to standard initialization and we compute from the inlet. We initialize, and when we go to run calculation, make sure that additional quantities are Mach number, total temperature, static pressure, total pressure, and density. Click OK. Number of iterations would be about 1000 to have a better results. Calculate. So we can see here that our calculation is done and we got a decent amount of error. Now we go to results. Now here we can see our wireframe of the nozzle. Now to define a contour, we add contour, select location at symmetry 1, and let's say our variable would be velocity. Click apply at the z axis, and you can see here our variation of velocity as the flow goes through the nozzle. Change this to 100 contours. You can see a smoother contour and a maximum velocity of 117 meters per second at the throat of the nozzle, which makes sense for a subsonic flow. So the flow goes in, it increases, reaches a maximum velocity at the throat, then decreases. Now let's say the variable would be Mach number. We would expect a similar behavior as velocity. So Mach number increases in the converging side, which is a maximum in the throat, and decreases. And we'd expect the pressure would act opposite in an opposite matter. So the pressure would decrease as it goes to the converging part of the nozzle, reach a minimum at the throat, therefore maximum velocity, and it increases. Pressure increases, so velocity decreases. You can see a minimum of 91 kilopascals and a maximum of towards our atmospheric, our inlet pressure. Now let's say density. Does it act similar to the pressure? And now let's go to location line 1, and we'll cut and apply. You can see we made the line in the center of the nozzle, so we can plot our values relative to the center of the nozzle. Let's go back and click on chart 1. Data series would be at line 1. X-axis would be the distance x. Y-axis would be, let's say, velocity. Click apply. Now we can see more accurately our velocity at the center, which is 0.5 meters, is at the maximum, which is around 120 meters per second. So it increases maximum and then decreases after the throat. Let's see Mach number, which is a maximum of almost 0.35 at the throat, of course. And let's see temperature. It would behave similar to pressure, so it has a minimum temperature of almost 292 Kelvin at the throat, then it increases. Let's see pressure. Let's see total pressure. Now it should be increasing after, it should be steady after the throat, since pressure increase almost steady. So you can see here, because static pressure increases whereas velocity decreases, so it will behave steady. The total pressure will behave almost steady since they cancel out. Thank you, and we hope you found this video helpful.